This is a video from the Exam 4 review, the Chapter 11 portion. Let's take a look at 15a. Suppose I want to use series to evaluate the limit as x goes to 0 of sine x minus x plus 1/6 x cubed divided by x to the fifth. Sine of x is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus ... Subtract x on both sides in this first equation. When you subtract x on both sides, that first term is going to go away. And so sine of x minus x is negative x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus ... And then what I want to do is add 1/6 x cubed to both sides. But keep in mind, 3 factorial is equal to 6, which means when you add 1/6 x cubed to both sides, this first term will now go away. And so what we end up with is sine x minus x plus 1/6 x cubed is x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial minus ... Now I'm ready to take a limit. So I want the limit as x goes to 0 of x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial minus, and then we keep going, divided by x to the fifth. If I split this fraction up, remember, x to the seventh over x to the fifth is x squared, right? And then x to the ninth divided by x to the fifth is x to the fourth, right? Laws of exponents. And so we get the limit as x goes to 0 of 1 over 5 factorial minus x squared over 7 factorial plus x to the fourth over 9 factorial minus, and then we keep going. Now, every term after 1 over 5 factorial has an x in it. And so all those terms will go to 0, and what we're left with is 1 over 5 factorial. And that's what we get down here. And so the limit as x goes to 0 of sine x minus x plus 1/6 x cubed over x to the fifth is equal to 1 over 120. And that's how we do 15a. Let's take a look at 15b. Suppose I have the limit as x goes to 0 of, I get x cubed minus 3x plus 3 arctangent x divided by x to the fifth. And I want to figure out what that limit is. Okay? Now, let's take a look at arctangent x. All right? Now, this is equal to the following. It's the summation from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1. And I want to write this out in expanded form. So what do we get when we write this in expanded form? We get, when n is 0, we get x. When n is 1, right, we get minus x cubed divided by 3. When n is 2, we get x to the fifth divided by 5. Then we subtract x to the seventh divided by 7, plus, and we keep going. So now what I need is 3 times arctangent x. So 3 arctangent x. Now I'm going to take every term and multiply by 3. So I get 3x minus x cubed plus 3/5 x to the 5th minus 3/7 x to the 7th, right? Plus 3/9 x to the 9th when we keep the pattern, right? And then we subtract and keep subtracting. Now, what I'm going to do is I'm going to add x cubed and subtract 3x to both sides. I'm going to add x cubed and subtract 3x to both sides. So we get something like this. Now, when that happens, I'm going to start at 3/5 x to the 5th. So I get 3/5 x to the 5th minus 3/7 x to the 7th plus 3/9 x to the 9th, and we keep going, okay? From here, I'm going to take the limit as x goes to 0 of. We took care of the hard part. The numerator is the hard part, in my opinion. So we get 3/5 x to the 5th minus 3/7 x to the 7th plus 3/9 x to the 9th minus. And I'm going to divide by x to the 5th. Now, when I split off this fraction, right, I get the limit as x goes to 0 of. I get 3/5 x to the 5th divided by x to the 5th. 3/5 minus 3/7 x squared plus 3/9 x to the 4th minus, and we keep going. Every term after 3/5 has an x in it. And as x goes to 0, all these terms will then go to 0. And what we're left with is 3/5. What does that mean? So the limit as x goes to 0 of. And then we get x cubed minus 3x plus 3 arctangent x divided by x to the 5th. This is equal to 3/5. And that's how you do 15b. 16, and then we'll look at a. Suppose we have the summation from n equals 0 to infinity of -1 to the n times x to the 4n divided by n factorial. And we want to know the function represented by this series. But what do we know? We know that e to the x is the summation from n equals 0 to infinity of x to the n over n factorial. Replace x with negative x, and we get e to the negative x is the summation from n equals 0 to infinity of -1 to the n, x to the n, divided by n factorial. Now, the last step, I'm going to replace x with x to the 4th. And so we get the summation from n equals 0 to infinity, -1 to the n times x to the 4th to the n, divided by n factorial, which is the summation from n equals 0 to infinity of -1 to the n, x to the 4n, divided by n factorial. 16b, So for 16b, we have the summation from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 divided by 2 to the 2n plus 1 times 2n plus 1. And what I want to do is I want to focus in on x to the 2n plus 1 divided by 2 to the 2n plus 1. And so this is the summation from n equals 0 to infinity of negative 1 to the n times x over 2 to the 2n plus 1 divided by 2n plus 1. Just laws of exponents. But remember, what is arctan x? Now, I think we just did that over here, right? Arctan x is the summation from n equals 0 to infinity of x to the 2n plus 1 divided by 2n plus 1 times negative 1 to the n, right? Let's see if we can make use of that. So the summation from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1. So I'm going to replace x with x over 2. And so our tangent of x over 2 is the summation from n equals 0 to infinity of negative 1 to the n times x over 2 to the 2n plus 1 divided by 2n plus 1, which is indeed equal to the summation, right, from n equals 0 to infinity and we get negative 1 to the n, x to the 2n plus 1 divided by 2 to the 2n plus 1 times 2n plus 1. And that's how we do 16b. Let's take a look at 17a. If I have the summation from n equals 0 to infinity of negative 1 to the n times pi to the 2n plus 1 divided by 4 to the 2n plus 1 times 2n plus 1 factorial. So we get the summation from n equals 0 to infinity of negative 1 to the n times pi over 4 to the 2n plus 1 divided by 2n plus 1 factorial. So it turns out this is equal to sine of pi over 4. So I need to see that first. And then this is equal to 1 over the square root of 2 or square root of 2 over 2. So I want exact answers, no decimal approximations. (17b), we get 1 plus natural log of 2 plus natural log of 2 squared divided by 2 factorial plus natural log of 2 cubed divided by 3 factorial, and we keep going, and this is the summation from n equals 0 to infinity of natural log of 2 to the n divided by n factorial. But if you notice, e to the x is the summation from n equals 0 to infinity of x to the n over n factorial. And so the only difference between these two series is if I replace x with natural log of 2, I get this series. And in fact, the correct answer here is e to the natural log of 2, which is equal to 2. So 17c. We have the summation from n equal 1 to infinity of negative 1 to the n minus 1 times 3 to the n over n times 5 to the n. And so I'm going to drop this to the summation from n equals 0 to infinity, right? So I want the lower limit to start at 0. But that means that n gets replaced with n plus 1. And you get negative 1 to the n times 3 to the n plus 1 divided by n plus 1 times 5 to the n plus 1. So I claim it'll be a little easier to see it in this way. All right? And this is the summation from n equals 0 to infinity of negative 1 to the n times 3/5 to the n plus 1 divided by n plus 1, like this. I hope that makes sense. Now, keep in mind something here, right? Couple comments. If I take 1 over 1 plus x, this is the summation from n equals 0 to infinity of negative 1 to the n, x to the n. So natural log of 1 plus x, right? This turns into the summation from n equals 0 to infinity of negative 1 to the n, x to the n plus 1 divided by n plus 1. Technically, you're supposed to add c here, but I claim I can show c is equal to 0 if I let x be 0. Okay? Now, doesn't this sort of look like this? But the only difference is I replace x with 3/5. And so the correct answer here will be natural log of 1 plus 3/5, which is natural log of a couple ways you can write this, but if you wrote natural log of 8/5, that's fine. Or natural log of 1.6, that's also fine. And that's how we would do 17. And we have enough time. I can look at number 14. So let's do 14, and we'll knock out that problem. So if I have the integral of arctan of x squared dx, what would I do, right? Now, remember, we've already talked about the power series for arctan x, right? The power series for arctan x is the summation from n equals 0 to infinity of negative 1 to the n x to the 2n plus 1 divided by 2n plus 1. So if we remember that power series, you can go right to it. That's fine. Now what I want to do is I want to replace x with x squared. So what I'm going to get is the summation from n equals 0 to infinity of negative 1 to the n times x squared to the 2n plus 1 divided by 2n plus 1 dx. So this is the integral from n equals 0 to infinity of negative 1 to the n, x to the 4n plus 2, right? Because I have to multiply those exponents, divided by 2n plus 1 dx. We're done. So this is equal to c plus the summation from n equals 0 to infinity of negative 1 to the n, x to the 4n plus 3, divided by 2n plus 1 times 4n plus 3, like this. And that's how we do 14. And that'll conclude this video for the Exam 4 review, problems 14 through 17. Thank you.